Hi everyone. Today we're going to study the definite integral. Let us define the definite integral. If f of x is a function defined on an interval, this is a closed interval from a to b. The definite integral of f from a to b is denoted as the integral from a to b of f of x dx. And it gives the area bounded by the curve y equals f of x, the lines x equals a, x equals b, and the x-axis. There is a note here. Although the notation for indefinite integrals may look similar to the notation for a definite integral, they are not the same. A definite integral is a number that denotes an area, while an indefinite integral is a family of functions. For illustration, we have this figure. The area A, it's here, the shaded region, is bounded by the curve y equals f of x. This is the curve. The lines x equals a and the x equals b and the x-axis. Again, the notation of definite integral is this: the integral from a to b of f of x dx. In here, we see two small numbers in the integral sign. We call this the limits of integration, the a and the b. Specifically, the a is what we call the lower limit, while the b is the upper limit. Now let us study properties of definite integral. This is the first property, the integral from a to b of f of x dx is equal to the integral from a to b of f of t dt. We may write also that this is equal to the integral from a to b of f of u du. Property number 2, the integral from a to a of f of x dx equals 0. We can see here that the limits of integration are the same. Property number 3, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Property number 4, the integral from a to b of f of x dx equals the integral from a to c f of x dx plus the integral from c to b f of x dx. Here, c is any number between a and b. Let's see now the fundamental theorem of calculus. We have this fundamental theorem of calculus part 1, and it goes like this. If f of x is continuous over an interval or closed interval from a to b, and the function capital F of x is defined by capital F of x equals the integral from a to x of f of x dx, then capital F prime of x equals small f of x over the closed interval from A to B. This theorem establishes relationship between integration and differentiation, and it guarantees that any integrable function has an antiderivative. Specifically, it guarantees that any continuous function has an antiderivative. This is now Fundamental Theorem of Calculus, Part 2. This is also known as the evaluation theorem, and it goes like this. If f of x is continuous over an interval, or we say closed interval from A to B, and the function capital F of x is any antiderivative of f of x, then the integral from A to B of f of x dx equals the capital F of x from A to B. This is the notation that is commonly used in some of the calculus books, and we can still evaluate this into capital F of B minus capital F of A. This theorem states that if we can find an antiderivative for the integrand, then we can evaluate the definite integral by evaluating the antiderivative at the endpoints of the interval and subtracting. Today, we're going to evaluate definite integrals. In evaluating definite integrals, say the integral from A to B of f of x dx, step 1 is evaluate this as indefinite integral. That is, the integral of f of x dx. And then the resulting is a capital F of x. This time, we will not add the c. Step 2 is, by fundamental theorem of calculus part 2, we're going to evaluate this function capital F of x with respect to the limits of integration. So we have f of b minus f of a. Example 1. Evaluate the integral from -2 up to 4 of the function x over 2 plus 3 dx. For step 1, let us integrate like indefinite integral. The integral of x over 2 is 1/2 times x squared over 2 plus integral of 3 is 3x. Then we multiply the denominators. 2 times 2 is now 4. We don't write the plus c because we will evaluate this from -2 up to 4. That is our step 2. That is, evaluate capital F of 4 minus capital F of -2. We have two groups. The first group, we evaluate this function using 4 minus we evaluate this function using -2. Now let's go to the next step. We simplify further. 4 squared is 16 plus 3 times 4 is 12 minus the square of -2 is +4. Then 3 times -2 is -6. 16 divided by 4 is 4 plus 12 minus 4 over 4 is 1 minus 6. The first group is 4 plus 12, that is 16, minus the second group, 1 minus 6 is negative 5. So 16 minus negative 5, this negative times negative becomes positive. That is now 16 plus 5. So we have 21. Example 2. Evaluate the integral from 0 to 1 of the function 1 minus 2x cubed dx. Let's evaluate like indefinite integral. Integral of 1 is x minus, we copy this constant 2, times integral of x cubed. That is x raised to 4 over 4. We simplify by cancelling this 2 and this denominator 4. 4 becomes 2 and this 2 becomes 1. So we have x minus x raised to 4 over 2. And as a rule, we don't use the plus c. Then we evaluate this from 0 to 1. That is the step 2. Evaluating capital F of 1 minus capital F of 0. There will be two groups. The first group is when we evaluate this function with respect to 1, minus we evaluate this function with respect to 0. In the second group, this is 0 minus 0 raised to 4 is 0, divided by 2 is 0. So all second group will be 0. That means we simplify only this first group. 1 minus, this 1 raised to 4 is 1. 1 minus 1 half is positive 1 half. Let's see this example 1. Evaluate the integral from negative 2 to positive 2 of the function t squared minus 4 dt. For our solution, let us evaluate as indefinite integral. So we have now the integral of t squared minus 4 dt, and we have the integral of t squared to be t cubed over 3 minus the integral of 4 is 4t. Now the step 2, we will evaluate the resulting function using the limits of integration. So we use the negative 2 and 2. Most of the books of calculus, you will see this notation. And this is the same with f of 2 minus f of negative 2. So the f of 2 is now 2 cubed over 3 minus 4 times 2. Then minus this f of negative 2 is the cube of negative 2 over 3 minus 4 times negative 2. We simplify the 2 cubed to be 8, then over 3 minus 4 times 2 is 8, minus, now the cube of negative 2 is negative 8 over 3. Then negative 4 times negative 2 is positive 8. Let us now remove the grouping symbol, and considering the second group is preceded by a negative sign, we're going to change the sign of the terms of the second group. So we have now this 8 over 3 minus 8 plus 8 over 3 minus 8. We will now simplify these numbers into negative 32 over 3. This is our final answer. Example 2. Let us evaluate the integral from 1 to 9 of the function x minus 1 all over the square root of x dx. For our solution, let us rewrite the integral and show that this radical sign here is a fractional exponent. So we have now the integral from 1 to 9 of the function x minus 1 all over x raised to the fraction 1/2 dx. And from here, let us distribute the denominator to each of the term of numerator. So we have this x over x raised to 1/2 minus 1 over x raised to 1/2. And let us simplify each of the fractions. So we have this x raised to 1/2 minus x raised to negative 1/2. And from here, let us do step 1, and that is to evaluate as indefinite integral. Using the power rule, this x raised to 1/2 is now equal to x raised to 1/2 plus 1 all over the denominator 1/2 plus 1 minus this x raised to negative 1/2 has the integral x raised to negative 1/2 plus 1 all over the denominator negative 1/2 plus 1. Simplifying further, this 1/2 plus 1 is 3/2. So we write here x raised to 3 over 2 all over 3 over 2 minus the x raised to this negative 1/2 plus 1 is positive 1/2. So we have here 1/2 as the exponent all over the same 1/2 as denominator. Let us simplify this further by flipping the denominator and making this denominator 2 to be coefficient of x in the numerator. So we have 2x raised to 3 over 2 all over 3. Then for this, minus 2x raised to 1/2. And from here, we will go to step 2. That is the f of b minus the f of a. And we say that in some books, you will see this notation, a vertical line, and we put the limits of integration, the 1 and the 9. So we have now 2 times 9 raised to 3 over 2 all over 3 minus 2 times 9 raised to 1/2. Then minus the f of a. We have 2 times 1 raised to 3 over 2 all over 3 minus 2 times 1 raised to 1/2. Simplifying further, this 9 raised to 3 over 2 can be simplified into 27. This 9 raised to 1/2 is 3. This 1 here raised to 3 over 2 is simply 1, and 1 raised to 1 over 2 is 1. You see here, the 27 and 3 can be simplified into 9, and 9 times 2 is now 18. Then minus 2 times 3 is 6. Then minus the second group now is 2 times 1 is 2 over 3. Minus 2 times 1 is 2. From here, let us remove the grouping symbol. So we have now 18 minus 6 minus 2 over 3 plus 2. So the final answer here is 40 over 3. Example 3. Evaluate the integral from 0 to pi over 2 cosine theta d theta. For our solution, let us evaluate as indefinite integral. So the integral from 0 to pi over 2 of cosine theta d theta is equal to sine theta. Then the step 2, capital F of B minus capital F of A. So the notation is here from 0 to pi over 2. So the f of b is now sine of pi over 2, then minus the f of a, that is sine 0. Let us evaluate the values of the corresponding sines here. But take note, in our calculator, it must be in radian mode. So the sine of pi over 2 is 1, then minus the sine of 0 is 0. 1 minus 0 is simply 1. This is the final answer. Example 4. Evaluate the definite integral x cubed minus 2x plus 5 dx from 1 to 2. Let's integrate like indefinite integral. The integral of x cubed is x raised to 4 over 4 minus, we copy the constant 2, then multiplied by integral of x, that is x squared over 2, plus integral of 5 is 5x. We can simplify the second term. We can cancel the 2 with the denominator 2. And finally, we have x raised to 4 over 4 minus x squared plus 5x from the limits from 1 to 2. Then, step 2, we evaluate f of 2 minus f of 1. This is our function capital F. So the first group will be f of 2. That is 2 raised to 4 over 4 minus 2 squared plus 5 times 2 minus the second group f of 1. 1 raised to 4 over 4 minus 1 squared plus 5 times 1. This 2 raised to 4 is 16 minus 2 squared is minus 4. 5 times 2 is 10. 1 raised to 4 is 1. 1 squared is 1. 5 times 1 is 5. 16 over 4 is 4. Then minus 4 plus 10 minus the second group. In the first group, the 4 minus 4 can cancel out. So the first group is simplified as 10. While the second group, we remove the grouping symbol. We change the sign of all the terms inside. So the 1/4 becomes negative 1/4, negative 1 becomes plus 1, plus 5 here becomes minus 5. Then we combine first the integers. 10 plus 1 minus 5 is 6, minus the fraction 1 over 4. Finally, the answer is 23 over 4. Example 5. Evaluate the definite integral x times x squared minus 1, then dx from 0 to 1. In the integration, we don't have product rule. What we do here is to simplify the product. So this x, we multiply to x squared, then to the negative 1. So we rewrite this integral as the integral of x cubed minus x, then dx from 0 to 1. Then we proceed with our step 1. We integrate. So integral of x cubed is x raised to 4 over 4 minus integral of x, that will be x squared over 2. Then we write the limits from 0 to 1. Step 2, we now evaluate f of 1 minus f of 0. This is our function capital F. So f of 1 will be the first group. That will be 1 raised to 4 over 4 minus 1 squared over 2 minus the second group, the f of 0. So we have 0 raised to 4 over 4 minus 0 square over 2. In the second group, because of the 0, all the members of the second group will be 0. Now we simplify the first group. 1 raised to 4 is simply 1 over 4 minus the 1 square is 1 all over 2. And the difference, 1 over 4 minus 1 over 2 is negative 1/4. Example 6. Evaluate the definite integral sine t dt from 0 to pi. Let's integrate sine t. That will be negative cosine t. Then we write the limits from 0 to pi. Step 2, we evaluate f of pi minus f of 0. So the f of pi is negative cosine pi minus the f of 0, negative cosine 0. We know the values of the cosine pi and cosine 0, or we can use our calculator. But make sure that your calculator must be in radian mode. So for the first group, we copy first the negative sign, and the cosine pi is negative 1, minus the second group. First we copy the negative sign, and the cosine 0 is 1. For the first group, negative of negative 1 is positive 1. So we write 1, and the second group, minus the negative 1. This is now plus 1. So 1 plus 1 is 2. Example 7. Evaluate the definite integral 8x cubed plus 3x squared plus 6x dx from 2 to 3. Let's integrate 8x cubed. The integral is 8 times x raised to 4 over 4 plus the 3x squared. We copy the 3, then integrate x squared, and that will be x cubed over 3 plus integral of 6x. We copy the 6 times the integral of x, that is x squared over 2. We can see that we can cancel some terms. So the first group is now 2x raised to 4 plus the second group x cubed plus the third term 3x squared. Then we write the limits from 2 to 3. Let us now evaluate f of 3 minus f of 2. This is our function capital F. So f of 3 is 2 times 3 raised to 4 plus 3 cubed plus 3 times 3 squared minus the f of 2. That is now 2 times 2 raised to 4 plus 2 cubed plus 3 times 2 squared. Let us simplify. 3 raised to 4 is 81. 3 cubed is 27. 3 squared is 9. 2 raised to 4 is 16. 2 cubed is 8. 2 squared is 4. Simplifying further, 2 times 81 is 162. We copy the 27. 3 times 9 is plus 27. Minus 2 times 16 is 32. We copy the 8. 3 times 4 is 12. Using our calculator, the first group here is 216 minus the second group 52. 216 minus 52 is 164. This is the final answer. Example 8. Evaluate the definite integral 12x cubed minus 9x squared plus 2 dx from 1 to 6. Let's integrate. The integral of 12x cubed is now 12 times x raised to 4 over 4 minus integral of 9x squared. we copy the 9 times integral of x squared, that is x cubed over 3, plus integral of the constant 2 is 2x. Then we simplify further. We can cancel some terms. The first term now becomes 3x raised to 4 minus the second term is 3x cubed, and the third term we copy the plus 2x. Then we write the limits from 1 to 6. In the second step, we evaluate f of 6 minus f of 1. So the f of 6 is 3 times 6 raised to 4 minus 3 times 6 cubed plus 2 times 6 minus 3 times 1 raised to 4 minus 3 times 1 cubed plus 2 times 1. The 6 raised to 4 is 1296. 6 cubed is 216. 2 times 6 is 12. 1 raised to 4 is 1. 1 cubed is 1. 2 times 1 is 2. Simplify more. 3 times 1296 is 3888 minus 3 times 216 is 648. Then we copy the plus 12 minus the second group. 3 times 1 is 3 minus 3 times 1 is 3, then plus 2. We simplify the first group as 3252 minus the second group is 2. So the difference 3252 minus 2 is 3250. This is the final answer. Today, we're going to evaluate definite integrals by substitution. Example 1. Evaluate the integral from 0 to t of the function t is square root of the quantity t squared plus 1 dt. First, we can show this square root as a rational exponent. So we have this t squared plus 1 raised to power 1/2. Then we decide for the f of x and g of x. F of x is the bigger function. This is the t squared plus 1 with the power 1/2. But for the f of x, there are two parts. We call the outside function, and that is the power, which is 1/2, and the inner function, which is t squared plus 1. So g of x is this function t. We collect now the u, and that is the inner function t squared plus 1. Let us take derivative of this. Du over dt equals 2t. Then we solve for dt. We cross multiply, so dt equals this left value. We need the two values, this t squared plus 1 and dt, for our substitution. For our function here, we write like this. The t squared plus 1 now becomes u, and the dt is now replaced by du over 2t. Now we simplify. We can see that we can cancel the t variable respectively. Simplifying further, we move this denominator 2 as 1/2. That is outside the integral symbol from 0 to t of this u raised to 1/2 times du. From here, we can now apply the power rule. We have 1/2 times u raised to 3 over 2 all over 3 over 2. We don't write here the plus c. We simplify this 3 over 2 denominator. We flip it up to be 2/3 to be multiplied with 1/2 times the numerator u raised to 3 over 2. For the two fractions, we can cancel the denominator 2 and the numerator 2. And the fractions are combined as 1/3. Then we return the value of u, that is t squared plus 1, that is raised to 3/2. From here, we evaluate this from 0 to t. That is our capital F of t minus capital F of 0. In the first group, since our upper limit is t, it is similar now to the function itself. Minus, now we evaluate this function using 0. Here it is. Let us now simplify. This 0 squared is simply 0. So we can remove this 0. Only 1 remains here. And this 1 raised to 3 over 2 is simply 1. We have here two groups and there is a common number. That is 1/3. So bring it out. We have now this t squared plus 1 raised to 3/2 minus 1. Example 2. Evaluate the integral from 1 to e of the function ln x over x dx. We have here two functions, ln x and 1 over x. For our u, we choose that ln x. Then we take derivative. du over dx equals derivative of ln x is 1 over x. When we cross multiply, solving for dx equals x du. We need the values of ln x and dx for our substitution. And we rewrite this integral now like this. The ln x we change into u, and the dx we replace by x du. We can now simplify by cancelling the x and x respectively. So our integral is simplified into the integral from 1 to e of u du. And then we apply our power rule. We have u squared over 2. We don't write the plus c. Then we retain the value of u in terms of x. That is our ln x, that is raised to 2 all over 2. Now we evaluate this from 1 to e. That is our capital F of e minus capital F of 1. Substituting the values, we have now ln e, that is squared, over 2 minus ln 1 squared over 2. This ln e can be simplified as 1. This ln 1 can be simplified as 0. In the second fraction, the 0 square is 0, divided by 2 is simply 0. So we can cancel the second fraction. For the first fraction, 1 square is 1 over 2. Finally, the answer is 1/2. Let's have this example 1. Evaluate the integral from 0 to 4, 2x times the square root of the quantity x squared plus 9, then dx. For our solution, let us rewrite this integral showing the radical to be fractional exponent. And from here, let us choose u. We let u to be this x squared plus 9. So du is equal to 2x dx. Let us now substitute these values to our integral. So we have this x squared plus 9 to be that u. Now we put the exponent 1/2. And this 2x dx is equal to du. Now let us evaluate the integral. Using the power rule, this u raised to 1/2 is now equal to u raised to 1/2 plus 1 all over 1/2 plus 1. The 1/2 plus 1 is 3 over 2. So we write u raised to 3 over 2 all over 3 over 2. Let us simplify this fraction here by flipping it up, making this denominator 2 be coefficient of the numerator. So we have 2 times u raised to 3 over 2 all over 3. From here, let us return the value of u with respect to x. We have this 2 times the quantity x squared plus 9 all raised to 3 over 2 all over 3. Now let us evaluate this with regard to our limits of integration with this 4 and 0. Starting with 4, we have now this expression minus this function evaluated by 0. Now let us simplify. This 4 squared is 16 plus 9 is 25. The 0 squared is simply 0 plus 9 is 9. So we write here 9. This 25 raised to 3 over 2 is simplified into 125, while this 9 raised to 3 over 2 is 27. 2 times 125 is 250. 2 times 27 is 54. We get the difference of the two like fractions. We have this 196 over 3. This is the final answer. Example 2. Evaluate the integral from 1 to 2, 6x squared times e raised to x cubed plus 1, then dx. For our solution, let us choose u to be that exponent of the e, the x cubed plus 1. So du is equal to 3x squared dx. Observing our function 6x squared, while here 3x squared. We want this 3 to be equal to 6. We will multiply this equation by 2. So we have now 2 du is equal to 6x squared dx. Now we are ready to do substitution. We copy the e, and the x cubed plus 1 is the u. So we see here e raised to u times the 6x squared dx is now replaced by 2 du. We have now this new integral of eu times 2 du. Let us simplify this first by putting the number 2 outside the integral sign. We have now 2 times the integral from 1 to 2 eu du. We know that the integral of eu du is simply eu. So we write 2 e raised to u. Returning the value of u from here, so we have 2 times e raised to x cubed plus 1. Now let us evaluate this with respect to the limits of integration from 1 to 2. Starting with 2, we have now 2 times e raised to 2 cubed plus 1 minus 2 times e raised to 1 cubed plus 1. This 2 cubed plus 1 is 9, so we have 2 times e raised to 9 minus this 1 cubed plus 1 is 2. So we see here 2 times e squared. We can factor out the number 2 from each term, so we have 2 times the quantity e raised to 9 minus e squared. This is the final answer. Example 3. Evaluate the integral from 1 to 2, 2x dx all over x squared plus 2. For our solution, let us choose u That is the x squared plus 2. So du is equal to 2x dx. Let us now substitute these values to the integral. So we have now the integral from 1 to 2. Our denominator x squared plus 2, that is the u. While the numerator 2x dx, that is du. The integral of du over u is simply the natural log of the absolute value of u. Let us return the value of u, which is x squared plus 2. So we have the natural log of the absolute value of the quantity x squared plus 2. Let us evaluate this with respect to the limits of integration. Starting with 2, we have now the ln of the absolute value 2 squared plus 2 minus the natural log of the absolute value 1 squared plus 2. This 2 squared is 4, 4 plus 2 is 6. So we have ln of the absolute value of 6 minus the 1 squared is 1, 1 plus 2 is 3. So we have the natural log of the absolute value of 3. Since we see here that the values 6 and 3 are both positive, we can remove the absolute value symbol. So we have this ln of 6 minus ln of 3. This is the final answer. Today, we're going to evaluate definite integrals using integration by parts. Let's have this example 1. Evaluate the integral from 0 to 3. X over the square root of the quantity x plus 1 dx. For our solution, let us rewrite this integral showing that the radical here is a fractional exponent. And then we will show this x plus 1 in the numerator. Thus, we will have a negative exponent. So we have now the integral from 0 to 3 x times the quantity x plus 1 raised to negative 1/2 dx. We can observe here that both of the functions are algebraic. Now let us choose u. In choosing u, let us select the one which is easier to differentiate. So we let u to be that function x, and the dv is equal to the quantity x plus 1 raised to negative 1 over 2 dx. So du is equal to dx. Then we take the integral of the dv. For the right side, we need to use substitution. So we let another variable w equals x plus 1. So dw equals dx. Substituting now the values, of course, the left side here becomes v equals, by substitution we have now the integral of w raised to negative 1/2 dw. Using power rule, we have now w raised to negative 1/2 plus 1 all over negative 1/2 plus 1. The negative 1/2 plus 1 is positive 1/2. So w raised to 1/2 over 1/2. Let us simplify this 1/2 by flipping it up, thus making this denominator 2 be coefficient of w. So we have now the value of V as 2 times W raised to 1/2. From here, let us return the value of W with respect to x. That is the x plus 1. So the value of V is equal to 2 times the quantity x plus 1 raised to 1/2. Now, let us use the integration by parts formula. Let us substitute the corresponding values in the formula. So we have the u, that is the x, times v, the value is 2, times the quantity x plus 1 raised to 1/2, and then minus. Now we show the definite integral from 0 to 3 of v, which is 2 times the x plus 1, and the quantity is raised to 1/2, and du is dx. Simplifying further, the u, v can be combined together, so we have now 2x times the quantity x plus 1, and this is raised to 1/2, minus. For the integral here, let us move the constant 2 outside the integral sign. So we have now this 2 times the integral from 0 to 3 of the function x plus 1, this is raised to 1/2 dx. For the integral here, we need to do another substitution method. We let a variable s be equal to x plus 1. So we have here the ds is equal to dx. Substituting now, we have the integral from 0 to 3 of this variable s raised to 1/2 times ds. Using our power rule again, we have the s raised to 1/2 plus 1 over 1/2 plus 1. This 1/2 plus 1 is 3 over 2. So we have s raised to 3 over 2 all over 3 over 2. Let us simplify this complex fraction. This 3 over 2, we're going to flip it up, then making this number 2 coefficient of the s in the numerator. So we have now 2 times s raised to 3 over 2 all over 3. This time, let us return the value of s in terms of x. So we have 2 times the quantity x plus 1 raised to 3 over 2 all over 3. And from here, this is the value of this integral. Let us do the substitution. Writing again the value of uv, and then minus 2 times this value now is substitute in here. Simplifying further, we multiply the constant 2 with that coefficient, so 2 times 2 is equal to 4, and from here let us evaluate this function with respect to the limits of integration. So we have now the first function here evaluated with respect to the upper limit 3, then minus this function evaluated in here using the lower limit 0. Observing this second group, the 0 here as factor will make this expression be equal to 0. Then let us simplify further. This 2 times 3 is 6, and 3 plus 1 is 4, and this is raised to 1/2. Then minus, we copy this 4, 3 plus 1 is 4, raised to 3 over 2 all over 3. And then this minus and minus here makes this positive. So we have 4 times 0 plus 1 is 1 raised to 3 over 2 all over 3. Simplifying further, this 4 raised to 1/2 is 2. This 4 raised to 3 over 2 equals 8. This 1 raised to 3 over 2 is 1. Now, this 6 times 2 is 12. The 4 times 8 is 32. 4 times 1 is 4. Simplifying 12 minus 32 over 3 plus 4 over 3 equals 8 over 3. This is the final answer. Example 2. Evaluate the integral from 1 to e. X raised to 4 ln x dx. For our solution, let us analyze the category of each of the functions. The x raised to 4 is algebraic, while the ln x is logarithmic. With respect to our order of priority, the islate, the letter L comes first than A of algebraic. So we use U as that ln x. So dv is equal to x raised to 4 dx. The du is equal to 1 over x dx. While we take the integral of the dv, we have now v equals x raised to 5 over 5. Let us now use our integration by parts formula. Let us substitute the corresponding values. The uv here is equal to ln x times x raised to 5 over 5. Then minus the integral of v, that is the x raised to 5 over 5, times the du, which is equal to 1 over x dx. Let us now simplify the uv into x raised to 5 ln x over 5 minus, let us move this denominator 5 outside, it becomes 1 over 5, and the integral of x raised to 4. So we simplify the x raised to 5 over x, and then the dx. We evaluate now this integral. We have x raised to 5 over 5. And simplifying this 1/5 times the 5 in the denominator here, we have 25. Let us now apply the limits of integration from 1 to e. Let us evaluate this function with respect to e, then minus evaluate this function with respect to 1. So we have now this expression minus this expression. Take note that ln of e is equal to 1, while ln of 1 is equal to 0. Substituting these values in here, respectively, we have now e raised to 5 times 1 over 5, then minus e raised to 5 over 25, minus 1 raised to 5 times 0, that is the ln 1, all over 5, minus 1 raised to 5 over 25. Simplifying further, the 0 here in the numerator will make this fraction equal to 0. So we have now this e raised to 5 times 1 becomes e raised to 5, minus, we copy this fraction here, this minus and minus becomes plus, 1 raised to 5 is 1 over 25. Putting together these fractions with a common denominator, we have now 5 times e raised to 5 minus the e raised to 5 we just copy plus 1 all over 25. Please observe that we can combine this 5e raised to 5 minus e raised to 5, and that is 4e raised to 5 plus 1 all over 25. This is the final answer. I hope you learned something from this video. See you again next time.